Okay, in this problem we are going to calculate the area of an ellipse and the volume of an ellipsoid, of a general ellipsoid like this, right? So let's begin with the area of an ellipse. This is easy. Remember, an ellipse is this shape. Okay, so it's got something like this. This is minus A, and this is minus B and B, right? Well, I've drawn the ellipse as if A is larger than B, but well, if it is the other way around, it would be like a form like this, right? Like a rotation of pi half by this, but that doesn't change the argument, right? What we have to do to calculate this is to calculate the area under this curve here and multiply by 2. And this curve, we have calculated it in the exercise before, is just b times the square root of 1 minus x squared divided by a squared. This is what you obtain from here when you eliminate y as a function of x, okay? You get plus or minus that, but the minus corresponds to this one. So we're going to calculate the area of this and multiply by 2. So the area of the ellipse is 2 times the integral from minus a to a of this function, which is b, the square root of 1 minus x squared divided by a squared dx. Okay, so that is 2b. And here we have a symmetric interval and an even function, so we multiply this by 2. So instead of 2, we'll write here 4. Okay, we'll write 4. And then what we have is the integral from 0 to a of the square root of 1 minus x squared over a squared dx. All right, the change of variable that we're going to use is similar to the previous problem. It's equal to that. Dx is a cosine d phi, and then what we have here is 4ab, right? This a and this b. Okay, and then we have the integral from, for x equal to 0, sine the phi is 0, for x equal to a, sine is 1, and therefore phi is pi half. Okay, and what we have here is a cosine, multiplied by this cosine is the cosine squared of phi d phi. 2 times the cosine square is equal to 1 plus cosine 2 phi. So this is 2ab times the integral from 0 to pi half 1 plus cosine 2 phi 2 phi d phi. Okay, this integral here is going to be 0, right? When we integrate it, as we have done this in the exercise before, so you can check that, the details. So this one here is pi half, so what we have is pi a b. Pretty much the formula of the area of a cycle. Remember, for a cycle of radius a, what we have is pi a squared. Well, an ellipse is like a circle stretch, and in which the two the two radii are different, a and b. So instead of a squared, what we have is the product a and b. That's the difference between the area of an ellipse and the area of a cycle. Okay, let's calculate now the volume of an ellipsoid. And to calculate that, what we have to do is to make cross sections. Okay, so what we're going to do is to apply Pappus theorem, and we make cross sections at a fixed value of z. Z can be any value between minus c and c, which is the range of values that it can take. And for any given c, z, what you have is x squared over a squared plus y squared over b squared is equal to 1 minus z squared over c squared. All right? Okay. Now we can divide the whole thing by this, and what we have is the following. We have x squared over capital A squared plus y squared over capital B squared equal to 1. Capital A is equal to A times the square root of 1 minus z squared over c squared, right? When you divide by this, you have a squared multiplied by that, and the square root of that is this. So you have here a squared. And capital B is the same thing with b. And the reason to write this way is because now you can see, well, a and b, of course, depend on z, right? But what you can see here is that the cross section at the fixed z is an ellipse, and the two semi-axes of this ellipse are given by this formula depending on what is the value of z, and z runs over this interval. Okay, so if it is an ellipse, we know the area of this cross section, because the area of this ellipse is equal to pi times the product of these two things, right? The two semi-axes is the formula that we have here. So we have a times b, and the square of this, which is 1 minus z squared over c squared. So we have the area of the cross section. And now we apply Pappus theorem, and the volume is calculated as the integral from minus c to c, so over the whole range of values of z, of the area of the cross section, which is this. And since this is a symmetric interval and the function is even, then we can reduce the interval to half of it and multiply by 2. And if we take out the constants, what we have is 2 pi a b, and the integral from 0 to c of 1 minus z squared over c squared, dz. All right? So that is equal to, it's just a polynomial, so it's 2 pi a b, and then we have z minus z cubed over 3 c squared. Substituted at 0 and c. For 0, this is 0, and for c, it's just c minus c cubed over 2 over 3 c squared. All right? Now c squared cancels with 2 factors c up here, and then we have c minus c thirds, which is 2c divided by 3. So what we have is 4 pi divided by 3 pi a b c. This is the formula of the volume of an ellipsoid, right? And now the last item in this exercise is, okay, what is the connection between this formula and the formulas that we have obtained in the previous exercise for the volumes of revolution of an ellipsoid? When you take an ellipse and you rotate around the x-axis and the y-axis. Well, when you rotate around the x-axis, what you're doing is you're duplicating the y-axis, so to say. So you have b equal to z. And the formula you obtain is 4 pi over 3 pi ab squared. And when you rotate about the y-axis, what you're doing is duplicating the x-axis, so you're making a equal to z. And then you have 4 pi over 3 pi a squared times b. So, and these are the two formulas that we have obtained in the previous exercise as a solid of revolution, right? This is the formula, the general formula, and you can see that these are particular cases of this formula here. The interesting thing about this is a problem that is complicated, like calculating the volume of an ellipsoid, is in general complicated, can be reduced to something that we can calculate because the cross-section is a non-figure. In this case, it's an ellipse. And we know the formula, we have actually obtained the formula for the area of an ellipse. So we can calculate the area of the cross-section, and given that and applying Pappus theorem, we obtain the volume of the final solid.